In the previous session, we have looked at how matrices help us in transforming the vectors. Now, continuing in the same thought, there exist certain special directions along which the transformation only scales the vector without changing its direction. The scaling transformation we have seen in the previous session. The scaling factor is called an eigenvalue, and the corresponding direction is given by a vector called eigenvector. If A is a square matrix and lambda is an eigenvalue of A, then there exists a non-zero vector such that when A is applied to the vector, the result is the same as multiplying the vector by a scalar lambda. In other words, A scales the vector and the resultant vector is a scalar multiple of the vector. The direction remains the same or reverses. That is parallel to the vector V. So how do we represent this? We say A times the vector is equal to the scalar times the vector. Here A is the transformation matrix, V is the eigenvector, and lambda is the eigenvalue. Eigenvectors are not unique. Any scalar multiple of an eigenvector is also an eigenvector corresponding to the same eigenvalue. So let's actually try to understand this, much more concretely. Remember, a vector can be represented as a single column matrix. Let X represent the vector V in matrix form. Then A times X is equal to lambda times X, where A is a square matrix. So here we have a lambda eigenvalue such that A times X, the transformation matrix times the vector, is equal to the scaled vector, scaled by lambda. Now this can be written as A times X minus lambda X equal to the zero matrix. Here, what is common? X is common to both the terms on the left hand side. So let's factor it out. A minus lambda. Lambda is a scalar. A is a matrix. So let's multiply lambda with the identity times X equal to the zero matrix, where I is an identity matrix of the same order as A. Now let A be equal to the matrix containing A11, A12, A21, A2, and X be the vector X1, X2 in matrix form. Now let's apply these matrices to this equation. We have A times X equal to lambda times X. I'm repeating the same thing. Here it was symbolic. Here we are using a generic version of the matrices and the vectors. So A11, A12, A21, A22 minus lambda times the identity of the same order as A times the vector in matrix form X1, X2 equal to zero matrix. Let's multiply lambda into the matrix. We get lambda 0, 0, lambda. Now let's subtract these two matrices. We get A11 minus lambda, A12 minus 0, which is A12, A21 minus 0, which is A21, and then A22 minus lambda. Now let's convert this into equation forms. A11 minus lambda times X1 plus A12 times X2 equal to 0. So this has become a homogeneous system of equations. And then A21 times X1 plus A22 minus lambda times X2 equal to 0. So we have system of collinear equations. Now, we have seen before, there exists non-trivial solution if and only if the determinant of a minus lambda I is equal to 0. So let's evaluate the determinant. We get a11 minus lambda times a22 minus lambda minus a21 times a12 equal to 0. Let's simplify that. Now let us name these coefficients of lambda using C0, C1, C2, where C1 or rather C0 is equal to 1, C1 is equal to minus A11 plus A22, and C2 is equal to A11 times A22 minus A21 times A12. Equation which we arrived at while evaluating the determinant becomes C sub naught lambda square plus C1 lambda plus C2 equal to 0. This is a quadratic equation, yes, but more generally it is a polynomial. This is called the characteristic equation or characteristic polynomial of matrix A. In general, determinant of A minus lambda I is equal to 0 defines the characteristic equation. Solving this equation, we get the eigenvalues. Since there could be multiple eigenvalues, I am putting it as lambda I. Now substituting the eigenvalues one by one into the equation A minus lambda I times x equal to 0, which is a homogeneous system, it will give us the eigenvector. In next two sessions, we will look at two problems related to eigenvalues and eigenvectors. That's it for now. Bye.